3, 2, 1. Beep.
Blast off. Happy New Year.
That's pretty good. Okay, so there was a rise in answer C. So let's see if I believe you guys. So the first term, what's 1/12 md squared? That looks to me like the moment of inertia for a rod rotating about where? Center. Okay. So this is 1/2 I prime, I about the center of mass, omega squared. So I think that answers to this term, plus 1/2 all the mass. Now what is omega d over 2? That would be, that would be the speed of the midpoint of the rod, which is where the center of mass is. So this would be 1/2 mv center of mass squared. So I like answer C. And, whoops. And so if I rewrite this expression using what we derived earlier for a rigid body rotating about its center of mass, then I could express this one as 1/2 I prime omega squared. And remember, as we discussed, if it's a rigid body and it's rotating, every point on the body rotates with the same angular velocity. Okay? So we have to be careful here. Why does this have to be I prime? Why do we need this? Why can't I just pick any random position for calculating my moment of inertia? Because then it's not going to translate into using this nifty theorem. We have to use the center of mass in order to get rid of this mess. Okay? So, yes, sir?
What if we just calculated I with the parallel axis theorem, and then did 1/2 I omega squared?
Is that one of the choices that I gave you?
No, but it's equivalent to C.
It is. It's true. Absolutely true. It's just not one of the options. Why? Since it didn't exercise what we were just working on. Yeah. Yeah.
So how is it translating?
How is it translating? So maybe not so coy. So this is a rigid body rotation about a fixed point. Agreed? Okay. So just as Josh said, I can use the parallel axis theorem, convert the 1/12 into 1/3, and it's just a pure rotation about the fixed point, so it would be 1/2 times 1/3 md squared times omega squared to get the kinetic energy. Yeah. That's totally correct. But if I look at it from the point of view of what's happening to the center of mass of the rod is there, and it's moving around an arc whose radius is d over 2. So I can also calculate the kinetic energy by summing up the translational kinetic energy of the center of mass and adding to the translational kinetic energy of the center of mass the kinetic energy of rotation with respect to the center of mass. Okay? Because sometimes, in fact, often, I won't have an object that's in a pure rotation. It will be some combination of translation and rotation. And we can then use this theorem to compute its kinetic energy. Yeah?
Why did we know that the angular velocity about the center was the same as the angular velocity about the end?
Clearly, my objects have not been big enough. So, every point on this object is going to rotate through the same angle if I rotate it. And it's true whether I don't move or whether I do. That was 180 degrees, regardless of whether I do this. Da, 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 right? So the translation is irrelevant. All points on a rigid body rotate the same. And it's not about just the center of mass. It's just the same. Okay? Good. I knew that one would come up.